Sir, good afternoon, sir.
Yes, good afternoon.
Yes, sir, we will begin shortly, sir. Good afternoon, sir.
Okay.
Shall we begin, sir, or should we wait for another 2 to 3 minutes, sir? Or
As you please. Yeah. It's up to you.
okay, sir. Okay, sir.
We want to wait for 2 minutes.
Swarna,
That's okay.
Good
okay.
afternoon, sir. I am Swarna from Department of Mathematics. Hope you remember me. You were
Yeah.
there for the national.
I, if I can see
Yeah,
your
yeah,
face,
yeah.
I will be able to remember. But yes, yes, now I remember.
Oh, yeah. You were there for our national seminar.
Yes.
Thank you, sir, for accepting our invitation and for being the resource person. Thank you very much, sir.
My pleasure.
Thank you, sir.
Ma'am, shall we start, ma'am? Swarna, miss? Shall we start?
Yeah, we can start.
Okay. So, yeah.
Yeah. Good afternoon, one and all. Today we are all gathered here to listen to the webinar on pure and applied mathematics, which today is our first session, and Professor Parameshwaran Shankaran would be taking us through it. And first of all, we'd like to close our eyes for a minute or so for a silent prayer. So let's all just close our eyes. Okay, so first of all, I'd like to welcome all of you here present, and over to Ms. Swarna, Department. Am I audible?
Yeah, you are audible.
Yes.
Yeah, okay. Over to Ms. Swarna, HOD of Department of Mathematics of Vimala College, to tell us more about Professor Parameshwaran Shankaran and to give the welcome address.
Thank you, Anne. Good afternoon, everybody. An equation means nothing to me unless it represents the thought of God. These are the words of the great Indian mathematician Srinivasa Ramanujan. His birthday falls on December 22nd, and all of us know that December 22nd is observed as National Mathematics Day. We are very happy to organize this webinar series in the month of December. First of all, I extend warm welcome to all to the webinar series on pure and applied mathematics organized by the Department of Mathematics, Vimala College Autonomous Thrissur, funded by DBT Star College scheme. The resource person for today's webinar is Professor Parameshwaran Shankaran from Chennai Mathematical Institute. He has done his BSc at University of Madras, MSc at IIT Madras, and obtained his PhD from University of Calgary, Canada. His areas of interest are topology, algebraic groups, and representation theory. Professor Parameshwaran Shankaran has more than 30 research publications for his credit. We had the privilege of having him personally for one of our national seminars. This time also, he readily accepted our invitation, and from the bottom of my heart, I thank you, sir, for being the resource person. He is a renowned mathematician, and we are really blessed to have him on the first day of the webinar series. Hope all the participants will be motivated by his talk. On behalf of Vimala College, DBT Star College scheme, and all the participants, I extend a very cordial welcome to you, sir.
Thank you.
I extend hearty welcome to our principal, Dr. Sister Beena Jose, who is the backbone of all our activities. I also extend warm welcome to Dr. Sister Sylvie Matthew, the coordinator of DBT Star College scheme of our college. We are glad to have participants from all over India. It is my pleasure to extend a cheerful welcome to you all. Once again, welcoming you all, I hand over the session to Professor Parameswaran Shankaran. Sir, please.
Thank you for the kind words and the invitation to give a talk here. So we still have about 3 minutes. Should we wait or should I start my talk now? Whatever you say, that I will do.
So you can start, sir. Most
Yes,
of
sir.
the participants have joined.
Okay. Yeah. Just one second. I put down some light. So I should say that I'm still not all that familiar with this technology of presenting talks using this virtual mode. So please bear with me. I'm going to share my screen with you all, and so that you can see what I will write. Okay, just a second, please. Can you see the screen?
Yes, sir.
Yes?
It is coming, sir. Yes, sir. Yeah.
Okay.
Yes, sir. It is fine.
So, all right. So, just one second. Yeah.
Yes, sir. Yes.
Okay. So, you can all see the title of my talk, Transcendental Numbers. Before I actually go into the technicalities, I should mention that I'm basically a topologist. I do not work in number theory. But I mean, sometimes you think about some problem involving topology or geometry, you will realize that you need to some number theoretic concepts naturally enter into the game. And in one such occasion, I came upon some results in number theory which I needed for my research, and that involves some theorem about transcendental numbers. Anyway, so I was fascinated by transcendental numbers, but sort of even the word irrational number, the first time you hear it, sort of scares you because of the something irrational. So somehow this association somehow creates some kind of a scare. But of course, the origin of the word is rational number. The word rational comes from ratio. And when you have a ratio, so we think of whole numbers. So P by Q. Q, of course, cannot be zero. P and Q are integers. When something is not a ratio, so it is a so when something is a ratio, it's a rational number. When something is not a ratio, you want to call it an irrational number. So so this is the nomenclature. But transcendental numbers are a little more than just saying irrational. And we all know examples of transcendental numbers. So E and pi naturally comes to our mind. Okay, so we begin formally. You see, the right context to state um, what is a rational number and what is an algebraic number and so on is working over complex numbers. So let me just begin with the very basic definition. By the way, this whole talk will be somewhat elementary. I understand that there's a large audience consisting of maybe students, teachers, research scholars, and so on. So it's a mixed bag. So the talk will be quite elementary, but there will be some deep theorems stated, not proved. And I hope to prove at least one theorem, at least to outline most of the proof of one theorem. This is the aim of the talk. So let us just begin by recalling some basic facts which perhaps many of you have already studied. Okay, so let us start. So yeah, so let alpha be a complex number. Okay, we say that alpha is algebraic or algebraic number, algebraic, if there is a polynomial p of x with coefficients from rational numbers. Okay, so this must be a non-zero polynomial. Okay, non-constant polynomial or non-zero polynomial, such that alpha is a root. So root of q. Root of p. I'll just erase. Okay. So it's a root of p of x. And what does that mean? That is, when you substitute alpha for x, p of alpha equals 0. Okay. And you all know examples of such things. Yeah. Let me try it out this way. I don't know if it will work. So I need to scroll up. So example, root 2 is algebraic because root 2 satisfies the equation x square minus 2 equals 0. So let's just write another example. I won't write too many. So I, we use it for square root of minus 1. Okay, is also algebraic since I is a root of x square plus 1 equals 0. Okay, x root of, we just say polynomial, not equal 0 when you write. Sorry. It's a root of this. Okay. Now the thing is, well, examples of, I will not be able to prove this. Examples of, I should say, before I even say what examples of, I should say a number and a number alpha in C is called transcendental if alpha is not algebraic. Okay, that is explicitly alpha is not root of any polynomial over Q. We just simply write like this. It means coefficients are from Q. We just simply say polynomial over Q. Okay. Now, so examples. Yeah, the famous examples are E. This is the base of natural logarithm. Base of natural logarithm. And pi, we all know. The proofs are not so easy, and we are not going to talk about proof of these well-known facts. Okay, but to write down some families of transcendental numbers, it's not so easy. Okay, you can cook up from known facts about E and pi several transcendental numbers using closure properties. For example, once you know E is this thing transcendental, E plus some any, so okay, E plus 1 or E plus root 2 is also, they are also, or even root of E are all transcendental. Okay. So you can also use pi and then play the same game. So pi minus 1, for example, or root 2 times pi. Okay. And so on. Root 2 pi, 2 plus root 3 times pi. You can cook up numbers like this and get new transcendental numbers this way. But you see, once you know one particular transcendental number, it's easy to generate such transcendental numbers by using some routine operations involving algebraic numbers. So formally, what we would like to say is, okay, some closure properties. So if we say, so denote by, I don't want to spend too much time on this, but go slow. Denote by, so tau, the set of all transcendental numbers, okay, then tau, well, see, is of course contained in complex numbers. I can think of complex numbers as a rational vector space. So this is a vector space over rationals. But question is tau a rational, a subspace, vector subspace of C? Answer is no. So tau is not closed under addition. Under addition. Okay. So why is it so? Well, you can just take pi plus minus pi, or for any transcendental number, minus of that also is a transcendental number, and this adds up to 0, and this 0 is of course rational. So it's not in tau. Okay. So this is not closed under addition. It is closed under multiplication of multiplication by a algebraic number. So if alpha, so this is the first property. Okay, second property, if alpha is in well, so we need a symbol for algebraic numbers. I should have introduced this. The symbol for algebraic number is q bar. Okay, if alpha is in q bar, actually it forms a field, the field of algebraic numbers, then yes, alpha plus alpha plus any, okay, so I'll write here alpha plus tau is equal to tau. Okay, so in other words, I take any transcendental number and then add alpha to it, that is again a transcendental number. In other words, what we call this property that tau is a union of affine spaces. Okay, by itself it's not a vector subspace, but it's a union of affine spaces. So that's why alpha plus tau is equal to tau. Yeah, so if alpha is not equal to 0, alpha is in q bar but not equal to 0, then so I take alpha times tau. This is again equal to tau. Okay, so well, you can say a little more. Suppose that alpha is a complex number such that, yeah, some polynomial, I take polynomial. This is equal to some, let us say, gamma, and gamma is in tau, where this polynomial p of x is a polynomial with coefficients from, I can take even q bar, no problem, q bar. Okay, so I only know after I apply this polynomial, this is in tau, then alpha itself is in tau. Okay, for instance, I could have taken polynomial x example. I can take, for example, this polynomial x square minus, let us say, x square minus 2. Okay, and substitute pi here. So suppose that, suppose p of alpha is equal to pi, then okay, I am saying that alpha is in pi. Alpha is a transcendental number. Okay, so what does it mean? Actually, you are just going to solve. How do you find such an alpha? So alpha square minus 2 must equal pi, and this is same thing as saying, okay, alpha square equal to pi plus 2, and this is like this implies that alpha is equal to plus minus square root of pi plus 2. Okay, so this is what I meant by performing this type of operations. You can generate, like I said here, you can take some, you can cook up always examples like root e. Okay, because root e is obtained by looking at it's a element alpha with the property that alpha square is e, and alpha square is e already implies that alpha is transcendental. So this is a type of thing that is involved when you say this. Okay, so the question is, can you go beyond these type of procedures and obtain, show first of all that there are lots of transcendental numbers. One thing I would like to point out is a cardinality argument. So I want to consider, okay, so I want to make this statement, there are plenty of transcendental numbers. What do we mean by that? Transcendental numbers. Okay, what do I mean by that? This means that, so plenty in what sense? So cardinality of tau is that of C. Okay. Number two, in terms of measure, also you can say. So topological property, tau is dense in C, or you can say the Lebesgue measure of tau is infinity. Okay, so all these points to the largeness of the set of transcendental numbers. In fact, everything, all these will follow because they complement. What is a complement? C minus tau, which is actually q bar. Okay, because by definition, what is q bar? Q bar is the space of all algebraic numbers, and tau is precisely the space of all numbers which are not algebraic. So the complement is this, and this is of course is countable. So what this means is that if you pick a number, complex number at random from C, almost certainly it will be a transcendental number. Okay. Nevertheless, we struggle to write down transcendental numbers. By the way, I don't know how many of you have seen this fact that a set of algebraic numbers is countable. Let me quickly give a proof of this because it's an important result. But at least if you don't remember after some time, whatever I'm going to say, this fact I think you should all know. So let's prove that. So q bar is countable. By the way, it's a basic fact that if you take C is uncountable. I remove only a countable set, namely q bar, and I'm left with tau. Okay, and therefore tau will be uncountable. So that is, it has in fact the same cardinality as C. And for the same reason, you take C, okay, and from there you remove any countable set, and what remains is a dense subset. So this second point would also follow if we prove this one. Same way, Lebesgue measure of any countable set is 0, therefore its complement has to be having the full measure. So Lebesgue measure of tau is equal to the Lebesgue measure of C, and that means that Lebesgue measure of tau is infinite. So all these three properties would follow if we just show that q bar is countable, and it's an interesting cardinality argument. So let us do this. What is q bar? Q bar is, I'll just be brief, set of roots of, okay, roots of polynomials with okay, so I'll just use the word over q. Okay, that means with coefficients from q. We all know that rational numbers is countable. Okay, so set of polynomials of fixed degree say n. Okay, this will be in bijection, but you know it's labeled by it's written once a polynomial, the coefficients are given. Okay, the polynomial is completely determined. So for each element of q power n plus 1, okay, you have a polynomial of degree n. Why q power n plus 1 and why not q power n? Because a polynomial will look like p of x degree n polynomial. This will look like summation aj x power j, and j is going from 0 to n. So there are n plus 1 coefficients are there. and this labels those coefficients. Okay, so if I give you these coefficients, that determines a polynomial. And how many elements are there in q power n plus 1? If q itself has cardinality, just that of the natural numbers, so this is again q power q square, q cube, q power n plus 1 for any finite n has cardinality that of the natural numbers. And that means that set of polynomials of fixed degree, which is in bijection with this one, has cardinality, has cardinality that of cardinality equal to that of natural numbers. Natural numbers, that is countable. Countable. Okay, so set of polynomials is countable, but given each polynomial there are only finitely many. So given a polynomial of degree n, okay, there are, well, at most n roots. There are, even counting multiplicity, there are n roots in complex plane, but we don't worry about multiplicity. There are at most n roots, ignoring multiplicity. Okay, and this means that, so if I give you, there is a, therefore now there is a way to label all the elements of q bar. Okay, so how do I do that? I just write q bar, which is equal to, okay, union over, so I have to write, give myself enough space. So here I will write here f, sorry, I don't want to use f, I want to use 0. So let's just write here 0. 0 z. So let me say zeros of p of x. Okay, now this p, okay, where is in q square bracket x. Okay, so now this is a, each one of these is a finite set. Okay, a finite set. Now this is a countable set. Therefore the union is countable. You see, when you have countable union of countable set, that itself is countable. But here I am having countable union of finite sets, so countable. So this shows that there are plenty of transcendental numbers. The problem is, so let me write down what the problem. So two questions or problems. There are two problems actually. One, write down. So plenty of, let me also say new. Not by just artificially translating a transcendental number by a rational number and so on. New transcendental numbers. So this is, I don't want to call it Q, I just want to say problem 1. And then second problem, problem 2. This is even more difficult. So given a number, alpha, decide whether alpha is in tau or not. Not in tau. Okay. So, remember, proving that pi is irrational is not an easy task. It was a non-trivial problem. It remained quite open for quite some time, and finally it was proved. The thing is, so there are plenty of numbers that arise naturally, and then one would like to know whether that is rational, irrational, and if it is irrational, whether it is algebraic or whether it is transcendental or what. Okay. So in general, so both these questions are relevant. So you see, this one is quite interesting. As we saw, almost all the numbers are transcendental. To write down plenty of transcendental numbers seems like a non-trivial task. Okay. So think about that. And problem two, I'll just give you some examples of numbers. So well, let me just write here e power pi and then just e plus pi. We are still playing with known numbers, okay? And then 2 power root 2. And then, so let us write, for example, 2 power pi. Let's write pi power e. Just standard operations. What about log 2 to the base e? A log always would mean to the base e, okay? Now, what do you guess? So you see, now we have written down some numbers. If it was a live classroom, I would take opinion, whether this number, for example, is transcendental or not, or what about this number, what about this number, what about this number, what about this number, okay? So you see, it turns out that this is transcendental and this is unknown. Okay, and this one is known to be transcendental. It turns out that, well, it's not clear whether this is transcendental or not, but we will see something about this. And this one turns out to be transcendental. Okay, so this is in tau. This is in tau. And it turns out that this one is in tau again. Okay, so but this is unknown. What is the thing? I mean, is it? Of course, one would think that it should be transcendental, but then what is the proof? We don't know. I do not know, and I don't think it is known. Okay. Uh, yeah. So you see, even with just very basic operations, you may be interested. See, you performed here only very basic operation of raising 2 to the root 2, okay, and it results in something transcendental. Okay, so so one would like to know some criterion for deciding. This is what I mean by saying this is a problem 2 is a difficult task, and problem 1 is perhaps not so, one should expect not so difficult. But then again, the very first attempt to come up with some list of uncountably many uh, transcendental numbers was achieved only, I mean, carries a name. It's a non-trivial theorem, and that's what I want to show. So let me just state the result that I am heading towards. Yeah, so the okay. So let me state this. This is a theorem. So before I state this theorem, I should say something about it. Let me state the theorem and then explain. Okay. Suppose that alpha is an algebraic number So that means it's a root of a certain polynomial, right? Algebraic number of degree n. Okay. Then there exists a constant C such that yeah, for any rational number p by q, and when I write p by q, always it means that q not equal to 0, p and q are integers. Okay, this I will no longer keep on repeating. It is hereafter be understood. When I write p by q, these are standard assumptions. Okay, for any rational number p by q, we have absolute value of alpha minus p by q is bigger than that constant. So constant c, yeah, c divided by q power n. Okay. Okay. So only thing I have not told you is what is this degree n. That same n is what is occurring here. So I should explain what this degree n means. So since alpha, so let me put a line here. I explain what degree is. Let px be so see px be a polynomial of smallest possible degree. See, alpha satisfies some polynomial of degree, some polynomial with rational coefficients. Therefore, it will satisfy a polynomial of smallest possible degree, and I am taking px to be one such. Px to be polynomial of least degree over q that alpha satisfies. Okay, so the degree, so degree of p of x is called degree of alpha. Okay, so that's the definition of degree of alpha. We all know that if you have a polynomial of smallest degree satisfied by a number alpha, that polynomial must be irreducible. Okay, p alpha irreducible over q. So you see, p of x has to be irreducible. It means that it cannot have root in rational numbers. It cannot be factored. If it can be factored, say like q of x times r of x, then p of alpha would be equal to q of alpha times r of alpha. But you know p of alpha is 0, therefore r of alpha is 0 or q of alpha is 0. But then q of alpha and r of alpha will have degree strictly less than p of that of p of x, and that is not possible because of the choice. We chose it to be the least possible degree. So p of x has to be irreducible. That means it cannot be factored. Irreducible over q. Cannot be factored into polynomials, two polynomials of strictly smaller degree, both having coefficients over q. That is what it means. Okay, irreducible over q. So, okay, now how? So I'll give a rough proof of this a little while later, but I want to say the following. So we will come to the proof of this later, but first I want to make some comments. So suppose that alpha is in complex numbers, alpha is such that there exists infinitely many rationals Pn by Qn such that, so there are, you can say infinite sequence if you want, such that you have this inequality. What is that inequality? Such that 0 less than P by Q, alpha minus Pn by Qn. Okay, Qn is less than 1 by Q power n. Qn power n. Okay. Then, well, we give it a name. We say that alpha is a Liouville number. Okay. You see, now theorem. If alpha is a Liouville number, then alpha is transcendental. Okay. Yeah. So you now have a way of at least trying to write down numbers. So you write down any number alpha with the property that you can approximate. How does one view it? You can approximate alpha by rational numbers P by Q, which are very close to alpha. What do we mean by very close to alpha? Look at this denominator, that same denominator, power n. And you should be able to do this for an infinite sequence. So that means that this number becomes smaller and smaller and smaller. So you can approximate alpha very, very closely by rational numbers. Of course, if you just don't say anything about, see, this bound here depends on this denominator. That's a crucial point. It depends on the denominator. Okay. If you don't say anything, you give me any, we all know rational numbers are dense in reals, or that's not a, so I should just say, sorry, even before I do this, let me say that here I am taking real numbers. Let me just do this. Yeah. So in this above theorem also I have to take, I probably didn't say it here, suppose in alpha in real numbers. Okay. All right. So I'm working with real numbers now. So if you can find a number alpha with this property, then this theorem tells you this is due to Liouville, and it tells you that this is alpha is a transcendental number. Let me give this a name or label, theorem 2. Okay, you will see that theorem 2 is a consequence of theorem 1. So here, let me give it a name, theorem 1. All right. So then how do we find Liouville's number? I will comment about proof of theorems 1 and 2, but before we go further ahead, let us write down some Liouville numbers, okay? And it turns out that it's very easy to do, okay? It's easy to write down, and then of course one needs to check that. So let's just you can do this over any base, but let us just work with the decimal numbers. Let an be in the set 0, 1, 2, 3 up to 9. Well, I can say I can allow an to be like this. I want to say an must be infinitely many of these ans must be on 0, but why not just simplify and then simply write here just 1, 2, 3 up to 9. Okay, I take this, okay, and consider summation alpha is equal to summation an by 10 power n factorial, not 10 power n, but 10 power n factorial. N is, so n bigger than or equal to 0, 1. Okay. So I take these numbers. You see, I have digits coming here, non-zero digits only when the decimal place is at n factorial for various values of n. Okay, so this is really thinned out. Okay, so for example, if I take a1 equal to a2 equal to a3, here of course I am just doing this for all possible n goes from 1 to infinity. I just wrote it like this. So let us take these all to be equal to 1. Then 1 factorial is 1, so 0. The number will begin like this, 0.1, and then 2 factorial is 2, so there is no problem. I have this 1 by 10 square, and then 3 factorial is 6, so 0, 0, 1. 1, 2, 3, 4, 5, 0, and then here at the 6th place, so I have 1, and so on. Okay, now of course this represents a number because you see this is compare with, I want anytime you write an infinite sum you must worry about convergence, but compare with the geometric series with summation. So what is the maximum possible value for an? 9. And here I have only 10 power n factorial. I may be just allowing all possible values of n. So I may just compare with this. Okay, 1. Now this is convergent. In fact, this is equal to 1. So these are all representing genuine numbers. Well, if you just write decimals also, it's clear that it represents a number. In general, you could use any base b bigger than 1, and then this will be convergent. Yeah. Okay. Now, so how many sequences? So for each sequence an, you have produced a number. Okay, and it turns out that these are all Liouville numbers. We will see that in a minute. Running out of time, but anyway. So then alpha is a Liouville number. Number for any choice. Choice of an, the sequence an. Okay. So I want to be able to just give a quick proof of this, even if I don't have time for proving the other two theorems. By the way, those results are theorems that I stated are due to Liouville. let's just write this. So I must produce rational numbers. You see, I must go back to the definition. Okay, I must produce these numbers Pn by Qn, which are really finely approximating my number alpha. And the most natural thing to do is use the partial sums. So let Sn be the rational number, summation k is equal to 1 to n, and then whatever you had, ak by 10 power k factorial. Okay, then this is a rational number, of course, finitely many terms, so no problem, it's a rational number. Now what is alpha minus Sn? This is whatever it is, it's going to be the tail end. Okay, this is equal to summation. So now this time k is equal to n plus 1 to infinity, and then here ak by 10 power k factorial, sorry, k, yes, k factorial. All right, now this starts off, so this starts off like this, an plus 1 divided by 10 power k plus 1 factorial, sorry, n plus 1 factorial, and then an plus 2 10 power n plus 2 factorial. Okay, and you can approximate this or rather estimate it. You know, this is at most each one of the numerator is 9, so I can just pull out and I can just say this is strictly less than 9 times. Okay, and then here 10 power n plus 1 factorial is common, so I may write here 10 power n plus 1 factorial. And then whatever you have here remaining, just replace that by geometric series. 1 by 10 plus 1 by 10 square, and so on. And you see here the crucial point is, okay, so this will, this is still maybe less than 9 by 10 power n plus 1 factorial. Okay, n plus 1 factorial minus 1 at the most. Okay, yeah, this you can sum and then can simplify this. Let me not worry too much. So this is what you get. Okay, let me just write here 1. You can show that this number is anyway less than thing. So let me erase that and write here 1 by 10 plus 1. Yeah, sorry. And then here I write just maybe 1 by 10 plus 1 n plus 1 factorial. Now you must compare this with what do you have there? Okay, the inequality for Liouville number 1 by denominator power n. Okay, and if you sum this, the Sn here, okay, Sn is written here, and you can estimate it. And when you estimate it, it is going to have, it cannot be more than, the denominator will be common denominator you can take, and that will be 10 power n factorial, and maybe there's a minus 1 there, and from there you have to show that. So I must if you just apply the inequality, I must compare n factorial, n plus 1 factorial and n times n factorial minus 1. This is what you need to do. And of course, which one is bigger? This is bigger. Okay, and this is what you will have if you have to through this inequality to show that. So this inequality shows that, yeah, so let me take so this shows that I wanted to say something more also, but this shows that, so what shows n plus 1 factorial is bigger than n times n factorial, maybe plus 1 there, I don't know. So shows that alpha is a Liouville number. Okay. Now, yeah, sorry. So something went wrong. Okay. So I'm here. Yeah. So the main thing is, when you have an algebraic number, it satisfies an inequality like this. Whereas if you compare this with the next theorem, okay, where we say that if this is, yeah, if this inequality is satisfied, then this is transcendental. So you see, if this inequality is satisfied, we want to say that, let me show this following. Suppose that this inequality is satisfied, okay, for any q, then I choose my q to be, see, this is true for any q. On the other hand, look at this inequality which I had pointed out here, okay, this inequality. Now if because there are infinitely many rationals, if n is very large, I would exceed this c. Qn will become larger than that c which occurs in here. Okay? And then q power, so I take some p n plus 1 by q n plus 1. So let me write here, squeeze in here. So take q, take n so large that see, there are only finitely many values of q such that it's less than c. C is q is positive, so large that c, okay, positive constant, c is less than q n plus 1. Okay, then I will have, on the one hand, I have alpha minus p by q, 1 by q n plus 1 in absolute value is less than, yeah, this is, if, okay, let's go back. So I'm trying to give a proof of this theorem. Suppose alpha were an algebraic number. I want to say that a Liouville number is transcendental. So suppose alpha is an algebraic number. Then what will I do? I will consider the degree. Suppose degree of alpha equal to n, then I can apply this inequality. That will be a constant c, such that this inequality holds good for all rational numbers p and q. But being a Liouville number, I have an infinite sequence, and in that sequence, denominator has to become large sooner or later, because there are only finitely many integers less than c. So I take a qn plus 1 such that qn plus 1 exceeds c. Being a Liouville number, I will have 1 by, this is q power qn plus 1 power n plus 1. Okay. But on the other hand, you see, this is strictly bigger than c by q power n. Okay. So if I take this q power n plus 1, what will this one say? This one says that alpha minus p n plus 1 by Qn plus 1 is strictly bigger than C by Q power Q. So degree is, and so I write here n plus 1. And that Qn, okay, sorry, I keep change. I did something and then something happened. Sorry. Anyway, not going to bother. So from that inequality, we get this. We see that any Liouville number. Yes, I got back the screen. So this inequality, I will have q power n plus 1 here, q power n plus 1, but 1q can be satisfied. This is bigger than 1 by q n plus 1 power n. So you see these two are incompatible, and that is the reason why alpha cannot be a Liouville number cannot be algebraic. Therefore, it is transcendental. Unfortunately, I ran out of time, and there I could not give a outline of proof of this. But before I leave you, I just want to state one result. I somehow didn't time my talk properly. I almost ran out of time, but let me just utilize couple of minutes I have to state this theorem. This is called the Gelfand-Schneider theorem. It says that if it's very easy to state, it's a remarkable theorem proved in 1934 independently by Gelfand and Schneider. So if alpha is not equal to 0 or 1, algebraic, and beta is algebraic but not rational, then alpha power beta is transcendental. So this way you get whole lot of numbers which are transcendental. Let me explain, give examples of this. I cannot go into proof or anything. Absolutely ran out of time. And the proof, this theorem is much deeper compared to the earlier theorem I mentioned. So forget about proof, but let's illustrate it. I take 2. 2 is neither 0 or 1, and root 2 is irrational, but it is an algebraic number. Okay, so it's algebraic but not rational. So therefore, by this theorem, we know that this is transcendental. Okay, now another thing. So you look at so I pi. Yeah. So yeah, I want to show that e power pi. So this is what I want to show. E power pi is transcendental. So this is over. E power pi is transcendental. How do we show this? So let me give a proof. Suppose that it's algebraic. Suppose e power pi is algebraic. Now I can take I. Take I. I is the I in complex numbers. Okay. Then this is not, it's algebraic. I is in Q bar, but not Q. Of course not. Therefore, e power pi power I will have to be transcendental. But let us compute this. This is equal to, on the one hand, by Gelfand-Schneider, this is transcendental. by Gelfand-Schneider theorem. On the other hand, you can compute it. What is e power I pi? E power pi whole power I is e power I pi, but e power I pi is minus 1. So this is Euler's identity. E power I pi plus 1 is equal to 0. One of the most beautiful formulae in whole of mathematics. So you see, so therefore this e power pi cannot be algebraic. Okay. So that is one of the things I stated at the very beginning of my talk. There are log 2 I mentioned. You can play this game with any natural number greater than 1. So you see e power, suppose log 2 again. Suppose log 2 is algebraic. Then look at e power log 2. By definition, log always means what? Means e power log to the base e of 2. But this is equal to 2. Okay? This is in rationals even. So in particular it's algebraic. But this cannot be. This implies that, yeah. So, how do I, yeah. So, yeah, sorry, this somehow doesn't show this, but let me stop here. I think I need to say something more to this. Maybe I can take e power, and I just got lost a little. Yeah. Let's prove this following fact. I don't know. This is a little bit complicated, but let's prove the following thing. Log 2 to the base 3, okay, is transcendental. I want to, yeah. I'm sorry, I got a little lost here. I'm not able to conclude this, but I can show the following thing. Log 3 to the base 2 or log 2 to the base 3, doesn't matter, is transcendental. How do we show this? So you just take 2 power. Suppose this were algebraic, then I would have log 3 to the base 2. This is equal to 3. Okay, but this is algebraic, and if this were algebraic, definitely this is not a rational number. That's easy to see. But the result is algebraic. So Gelfand-Schneider theorem will tell you that if log 3 to the base 2 was algebraic, then that would be transcendental. 3 would be transcendental, which is absurd. So this is transcendental. At least we are able to say this. I think my time is up, so I should stop. So I'll stop sharing screen. Yeah. And if you have any questions, maybe you can ask. Sorry, I couldn't sketch a proof of the theorem that I wanted to say, but anyway, I'm out of time. Yeah.
Sir, it is already 3.
Yes.
5.
Yeah.
Yes, sir. But if it is okay for the participants, we can, I hope. Swarna miss?
It depends. If sir wants to continue, he can continue for 15 odd minutes.
Yes, sir.
Sir?
Are you sure? I can just maybe very briefly sketch a proof of that theorem. I think that theorem is very much accessible. It involves only mean value theorem. So I go back to that and try and do this. Okay.
Okay,
So
sir.
I'll try and
Definitely.
just take 10 more minutes, not more than that, and sketch a proof of that.
Of course, sir.
Okay, sir. No problem.
Share. Okay. Yeah. Let's take a new page. I'll just take a new page and complete my talk. So let's just quickly recall alpha. I'll write briefly alpha in Q bar, that is alpha algebraic. Degree of alpha is equal to n, implies there exists a constant C positive such that for any P by Q rational, yeah, Q not equal to 0, Q positive, etc. Absolute value of alpha minus P by Q, okay, is less than, sorry, it's not less than, it's greater than. It is. Is greater than, yes, is greater than C by Q power n. Okay, so I want to sketch a proof of this. So let me do this quickly. So by definition, there is a polynomial. So I will say there exists an irreducible polynomial, smallest degree. So irreducible polynomial of degree n, say P of x, such that P of alpha equals 0. This is what we know. Okay, and this is a basic thing. So so we may assume irreducible polynomial over Q. So by clearing denominator can assume all the coefficients or in integers. So it's an integer polynomial. Okay. And now the important thing is there are two inequalities. Let me get to the crux of the matter because we are interested in this alpha minus P by Q. Okay. First of all, so this is the first remark. P of P by Q is not equal to 0. If it was equal to 0, then you will be able to factor out x minus P by Q. But then P was a irreducible polynomial, so that's not possible. Okay. Now consider this. So you see P of P by Q. I can rewrite it as P of. It's a really remarkable thing. Just a small trick, but it gives you a nice answer. Minus P of alpha. Okay. But by mean value theorem, this is always P by Q minus alpha times P dash of some number xi between. So let me just say here is alpha and here is P by Q and xi is somewhere here. Okay. We don't know. In between. It could be that P by Q is on this side, doesn't matter. Let's not worry about such details. And so you get an inequality. Well, first of all, equality, P by Q, whatever we want, we'll have here. This is equal to P of P by Q divided by P dash of xi. Well, I have to write that here. Okay. You see, because this is not equal to 0, neither of these factors are 0 and therefore division by P dash of xi is valid. Now, let me at least show one. So we have to estimate. Okay. So I tell you, if you write P of x, P of P by Q, let's just write that. P of P by Q, this is equal to summation AK P power k Q power minus k, right? So I write that denominator Q power k. Let me write that Q power k, and of course this is a finite sum, k equals 0 to n. And now this 1 by Q power n can be pulled out, and then here whatever you have, that's going to be an integer, an, so ak, p power k, q power n minus k, and this is an integer. And it's not equal to 0 because this side is not 0. So this is at least in absolute value if I have, okay, I forgot absolute value here. And here also absolute value. Now in absolute value, if I put that here, is at least 1, okay, because it's an integer and it's not equal to 0. So this is, I can say, bigger than or equal to 1 by q power n. And that is that 1 by q power n which is coming in the statement of this c by q power n, you see that 1 by q power n. Now all that which remains is to estimate this quantity here, and for that what you need to do is, first of all, one remark is that you need only consider this interval p, yeah. So you see, you consider alpha minus 1, alpha plus 1, okay, because if you have a rational number p by q, somewhere within here itself you will be able to find a rational number p by q which is closer. See, if p by q is outside, I drew the diagram here. You see, I need only look at those which are within distance 1 on either side of alpha. If the p by q lies here somewhere, then you just subtract 1 and move closer. If it lies here, add 1 and moves closer if it is outside this stage. So you can always come close to alpha. Anyway, okay. So when you do that, you need only estimate this within this range. And within this range, you know, it's just, so if xi is in here, okay, then this is the important thing, mod xi is less than or equal to mod alpha plus 1, mod alpha plus 1. And now you write the polynomial that gives you you can write p dash of xi. This will be whatever it is, and I am interested in computing absolute value. This is less than or equal to summation. You know the formula for derivative, right? You just write that p n times, k times x power. So you see xi power k. I am going to write here. I have to rush a little. Mod xi power k minus 1. Let us not forget the coefficients a sub k. And this is a finite sum. And now for this, you substitute this and get an inequality. Okay. Okay. So this is less than or equal to some number and put that number here. Okay. So summation k times mod alpha plus 1 whole power k minus 1 times mod ak. And all these quantities are all non-negative, and constant term is not equal. Yeah, leading term is not equal to 0. So you can show that this is possible. So this is what we want to take. This you take it to be a, and in fact strictly less than. So here actually not equal to, because xi is in the interior of the interval if you apply that Rolle's theorem or mean value theorem. So that gives me the required inequality. I can go back and substitute here. Substitute that a over here, and I will because I am substituting by a lower thing. So this is bigger than so the numerator I bounded it by 1 by q power n, and denominator I have this number a. So this 1 by a I can take it to be my c. That's it. That's all the proof, and I'm done. Okay. So I'll stop sharing. So this proves the inequality that we wanted, and this is at the heart of producing Liouville number, and I'm done. Sorry, I exceeded time, but I hope some ideas were conveyed, and you learned how to write a new transcendental number, whole lot of families of transcendental numbers. Thank you for your patient listening. Sorry, I exceeded time.
No, it's okay, sir. Thank you, sir.
You're welcome. So it has been enjoyable, and I thank Dr. Anjali Kishore for inviting me to give the talk once again. Yeah.
Thank you, sir. It was our privilege, sir. Thank you, sir.
Okay.
Thank you, sir. Thank you. Over
So
to Anne.
you can.
Anne, yeah.
Yeah. So, anybody out there has some doubt? Sir is free now. You can ask him. You could either put it in the chat box, or you could just ask him directly by unmuting your video and your audio.
So I must mention that there is this book by Nivan, Irrational Numbers. That's a very nice book. It's a classical book. So people who have access, and there are many more books and research papers. And you can even Google and find out a lot of information and references for everything that I talked about. And people can send me email if they have some question. No problem. Okay, you can find my email by going to see my web page.
Okay, sir. Thank you. Very kind of you. Thank you, sir.
You're welcome. Okay, bye.
Sir, we have a short vote of thanks, sir. Could you wait for another 2 minutes, sir?
Okay.
Okay.
Sure.
Yes. Now I invite Ms. Viji from Kerala Verma College.
Good afternoon, dear teachers and my dear friends. I have a very little knowledge about transcendental numbers. Today's class makes me curious about these numbers. And the word, when I Google about the transcendental numbers, I got the word meaning of transcendental. It means supernatural. That is something related to non-physical world. Here also we have a very supernatural teacher for explaining the topic. So I sincerely extend my gratitude or our gratitude to you, sir, for such a nice class. The class was extremely useful. Also, I extend our heartfelt thanks to Department of Mathematics, Vimala College, Thrissur, especially to Miss Swarna, Miss Dolly, and Miss Anjali for my teachers. We are eagerly waiting for the other sessions of this webinar series. Thanking you, especially sir. Thank you once again. Thank you.
Okay. Thank you and bye.
So once again, thank you, sir. Thank you.
Namaste.
Thank you very
Thank
much,
you.
sir. Thank you very much.
My pleasure.
Thank you, sir.
Thank you, sir. Thank you.
And thanks to all the participants for your valuable time. Thank you.